We have the sheets of metal. We have a brick cut out of that. Now we add there two contacts. And if we apply some voltage on that, we would realize strange things. First, you could cut it in a manner in which there will be no current. If I just cut it in this shape, we have something which would not be conductive. But in this case, there is some current, so I will measure that there is current flowing through that. But if I have a means to investigate the direction of the current, I would be quite surprised, because I apply voltage in this direction, from here to here, exactly. But the current has this direction. So the cause, the voltage, and the result, the current, are not collinear. They have different directions. And that's strange. That's something we do not have direct experience with in our everyday life. This is why such a kind of material is so strange to us. So this is strange. Now, in such an artificial material, we would get the result dependent on the direction of the cause. And that is first strange, unusual, and difficult for any computation. Although you might be surprised, we use such materials intentionally, and we use those materials, for example, in microwave circuits to create strange things like transmission lines that guide the wave or the information in one direction but not in the other. We will talk about that later, and I will show you some examples or some samples of that. But anyway, a material which is not isotropic is called anisotropic. Well, this is a poor example for education. If you wanted to get to some real example of an anisotropic material, you have it over your heads. The ionosphere is anisotropic, at least as to electromagnetic field, and some ferrites are anisotropic. So we will later show what that means for electromagnetism. But now I return back to the last slide to define the playground at which we will play the game. So first, we have four ways of distinguishing materials or classifying materials. That's stationary and non-stationary. That's against time. Linear and non-linear as to the response. Homogeneous and non-homogeneous as to the behavior of properties at the different points of that material. And isotropic and anisotropic as to behavior of the material, on the material properties in different directions. Now, let us make an agreement that, unless otherwise mentioned, we would only talk about stationary, linear, homogeneous and isotropic materials during this course. You will see that anyway, even then, it is difficult enough. So from now on, we think about stationary, linear, homogeneous and isotropic materials. There is one more point that I have to clear at the beginning of the course, and that is the question of measure or size. In many cases, we would use differential approach or derivatives. And a derivative is, by its definition, the increase of a function divided by the increase of the variable, the increase of a function value divided by the increase of the variable of the function, but it's taken as a limit for close to zero increase in the variable. Now, that's a very nice mathematical construction, and there is also a problem in it. And that problem is a little bit hidden. Well, let's talk, for example, about this marker. It's a whiteboard marker. It's inhomogeneous. It consists of a cap, a tip, a refill inside, the body. It is mostly plastic, although there is some water and some alcohol and some dye in it. But what if I, for example, want to get inside? If I have a magnifier glass, so I get a magnifier glass, and I would be able to inspect the surface of that body of the marker much closer. Well, okay, but what if I want to get much better approach? For example, what if I wanted to repeat the Archimedes determination of specific mass of that body? So I would have to measure the volume and I would have to measure the mass. If I do that, I can divide mass by volume, so I have the specific density as a mass divided by volume. Well, but we will have problems with the marker. As you can see, it's not composed of one material only. There is the tip, which is clearly a different material from the cap. And there is the refill inside, which would be again a different material. So if I want to measure exactly and get, for example, the specifications for the cap, I could not just measure the whole marker. I would have to get a small piece of that, a piece of the mass divided by a piece of the volume. That's a good way how to get better results. Now, scientists have developed excellent measures to measure mass and volume, so we would get a small tiny pieces of that. And the mathematicians can even say, okay, but we can change the elementary volume into a point by using a limit of delta V approaching zero from the right side. Well, that is true, but what, for example, would happen if we have the cap and try to use the mathematical approach to the very end? Well, first we would have a cap, we can weight it, we can measure the volume, for example, by immersing it into water like Archimedes and measuring the change in the water level. We can do that with smaller and smaller pieces of that cap. Well, after some time we get to very small measures like micrometers, and still everything works. Well, if we divide that small volumes into nanometer scale, first at 100 nanometers we would have no problems, but going down and down we get to a problem, because at the end of nanometer scale we would get to the size of the molecule of the plastics. And now if we divide it we will have some piece, but that will not be the same kind of material if we divide one molecule into pieces. But further on, if we go with delta V to 0, we will get to subatomic distance. And now we will have a real trouble, a real headache, because mostly we would measure a space where there is nothing. Sometimes we would just catch an electron, and that would be quite heavy. But sometimes, very, very rarely, we would get to the atomic nuclei, and we would get very big mass per volume, like in neutron stars. That would be absolutely crazy. I mean, we mostly use specific density to calculate the mass of a bigger thing. So if I know that the specific density of concrete is, say, 4,000 kilograms per cubic meter, and I know that the pyramid has 1 million cubic meters of volume, I can say, okay, the pyramid would be 4 billions kilogram or 4 million tons. Well, that's fine, but that works for the pyramid. If I want to get the same meaning and I go to very small volumes, it does not work at all, because I have reached the atomic nature of matter. I am somehow playing with quantum physics, and it's a complete nonsense. So we have to make another agreement, not only stationary, linear, homogeneous and isotropic materials, but we will only study objects that are big enough. So even if I use differential operator, I mean that something that the differential is using a very small volume but big enough to cover several molecules of the material. Otherwise, I would get into quite funny troubles that are somehow connected to the quantum nature of universe. There is a special course in electromagnetics that tackles quantum, that's quantum electrodynamics, but we will not cover this in this course. It's something that is quite advanced, and we for the moment forget about quantum effects. So this is somehow establishing our playground. Now, if I may point that this is very convenient. We have defined the playground so that we have only simple materials, and we have got rid out of any quantum effects. Well, I hope that this would be fine for you, for your whole professional life, but I'm not sure in it. Why? Well, for example, processors in my arm watch or in my mobile phone, at the time being we are switching under 10 microns of conductive paths. So we, at least Samsung and other companies, are declaring that they will have 5 nanometer process soon in production. Well, that's very fine, but what does that mean? You have a conductive area, a wire, and the dimension is only some tenths of atoms. This is very convenient because you get low consumption, you get very high integration, but also with decreasing the dimension even more, and it will be physically manufacturable soon, you get some troubles. For example, the current is so small that you will have fluctuations in it. If you have, let's say, so I can't erase. So please just let's use this space. If you have 3 wires in classical circuit theory, you have 3 currents, I1, I2 and I3. And the classic, that is non-quantum rule, says if you feed some current into this wire, the sum of currents in those 2 wires should be the same. So I1 is I2 plus I3. Well, this is true if you observe long enough, that is, you do not have to use a high clock frequency, or if there is a lot of current. But decreasing the dimension of the conductors, decreasing currents to save power, you can get to a situation when at some time all the currents are flowing in the same direction. Well, in average, still the law holds, but at a certain moment you can violate it. You are reaching quantum effects. I wanted to mention it just at the beginning. I don't want to threaten you. This is not what we shall talk about. But I just wanted to mention it because it might happen that sometimes in your professional career you might reach the boundaries between classic theory and quantum theory. It's just important to know that there is a boundary. Then there is something which behaves quite unbelievably. Dear colleagues, ladies and gentlemen, it's time for your questions. It is still time for your questions. Okay, so we have set up the playground as to time, as to linearity, as to homogeneity and isotropy of the material. We will now start the second part of today's lecture, which will really be touching electromagnetics. Within the playground, we have specified in the first part. Now I promised you to take a break so that we shall meet again at this place at 9:45. And please, if you have some questions, we will start with the questions. So, see you for a while.